Okay, so this is an introduction to limits with multivariate functions. It's going to be a bit of a long video and kind of real mathy technically, so just kind of bear with us as we're working our way through this. So in order to get to the idea of a limit, we first have to have the idea of distance in an n-dimensional space. Okay, so if I have two things which are both in that space, right, where let's say x is x1, x2 out to xn, so it's an n tuple, and y is y1, y2 out to yn, it's also an n tuple, right? And we have some function d that eats x and y and does a measurement here, okay? So it takes component by component and it subtracts them. So it's x1 minus y1 squared, x2 minus y2 squared, and then we go all the way out to xn minus yn squared, right? This is going to give us some scalar. Then we say that d of xy is the distance between these objects in Rn called x and y. So now we've made a good solid definition for what a distance is. So let's get an example of using that. Okay, so let's say I have x is at 2, 1, 4, so that's in R3. Y is in -1, 3, 7. It's also in R3, so I want the distance from x to y. This is going to be the square root of 2 minus -1 squared plus 1 minus 3 squared plus 4 minus 7 squared. Let's see, what's that going to give me? This is 3 squared plus -2 squared plus -3 squared. So this is like the square root of 9 plus 4 plus 9, which is the square root of 22, which is approximately 4.69. So the distance between these things has an approximate value of 4.69 in 3 space. So we have a functioning definition that given two things in a particular n-dimensional space, I can find the distance between them. Okay, we're going to create an object that I'm going to call a delta ball. Okay, and this is also going to be in our n, right? So x is going to be something that's in Rn, and then delta is going to be some real number such that delta is positive. Okay, so we're going to define this b. B is going to eat x and delta, so something in Rn and a real, and it's going to return a set. It's the set of all y which are in Rn such that dxy, so the distance between x and y, is strictly less than delta. So this gives me like a ball of objects that has a radius of delta that's centered at x rather. So this is a delta ball about x. So we call bx delta the delta ball about x. So like this is x is here, and I have some sort of n-dimensional, so x is here, I have some sort of n-dimensional sphere that has a radius of delta, and anything inside that sphere has to be delta or less away from x. So now that I have distance, I have the way to stretch a ball around something. Okay, so finally I can define a limit. Now I'm going to build the limit in R2, but this can be expanded into Rn. There's no reason why it can't be. So if for every epsilon greater than 0. So basically you have this two-player game. The epsilon player is going to pick an epsilon. We need to pick a delta that's also bigger than 0. And I have some point AB, which is in R2. Now that could be ABC in R3. It doesn't matter. It's still going to work. And if XY is also some point in R2, right, such that, okay, so we're going to put XY in a very particular place. XY is going to be in the delta ball around the point AB. So there's where our delta ball is coming in. So we're going to center the ball at AB. It's going to have D, and XY is going to be inside that ball. Okay, so if I'm inside that ball, if that implies that f of xy minus L is less than epsilon, then we say that the limit as xy approaches AB of f of xy is equal to L. Alright, so this is like very similar to the limit definition we used for two-dimensional xy functions, f of x equals y functions. However, now because, so in that you can only take a limit coming from the left or from the right. But when we're now in like three-dimensional space, you could take a limit coming from any direction. So what we do is we stretch a ball around the point, and then we make the ball closer. And if I can make the ball closer, I can make the limit hit any given epsilon. So there's a couple of visualizations of this that we're going to try here, and we'll see if we can get there. Okay, one is like a kind of a two-part visualization. So we've got the xy plane here, so this is R2, and I have my domain, we'll call it D, and I have a point AB inside that domain, and what I want over here in R is I am going to say this. Here is L, right? And the epsilon player is going to give me a range around L which I have to hit. So this is L plus epsilon, and this is L minus epsilon. And the argument is that can I stretch a ball around AB? So like in R2 it's just a circle, right? That has a radius delta. So can I pick a delta so that every time I have a point inside here, let's call this XY, that point is going to map by F into something that's in this range between L plus epsilon and L minus epsilon. And if I can keep making epsilon smaller, and I can keep finding a delta that makes a ball that maps between those two epsilons, then I can say that the limit as xy approaches AB has the function going toward L. Okay, so think about that for a second. That's how you would do this with two pictures. One picture in R2, the domain, and the codomain is R. And what we do is by keep shrinking the ball over here, we hopefully are keep shrinking the range. And if we do that, this is eventually going to map toward that. As we get closer and closer to this inside the ball, this is getting closer and closer to L. So as xy goes to AB, f of xy is going to L. Alright, there's a three-dimensional way to visualize this. I think it's a little more cluttered though, right? So now we have the domain on the floor here, right? And in there's a point AB on the floor, and we're going to stretch a delta ball around that on the floor. So there's D, right? And then we have like some surface above this. And we're going to say that this point here, right, directly above that, its value here is going to be L. And what we want to say is that if I have a point inside that circle, x, y, the height here of that same circle has to be between L plus epsilon and L minus epsilon. So that when x, y comes up and strikes here at f of x, y, I'm within that range of height. And ultimately, as this circle gets smaller, this epsilon can get smaller, and eventually I'm going to approach the height that L is at. So we're going to say that as xy gets closer to AB, the height is getting closer and closer to L, and that gives me the idea of a limit. Okay, so a couple of different visualizations, and we'll work from there. So proving that a limit does not exist is actually kind of easy. Just like before, if I could show that the limit from the left and the limit from the right did not agree, I knew that there wasn't a limit. So I need to find a limit from two different directions that comes to two different numbers. So let's take a look at the limit as xy approaches 0, 0 of x squared minus y squared over x squared plus y squared. The argument is that this limit does not actually exist. Okay, so let's try this. Try taking the limit along the x-axis. So x can change, but y is always going to be 0. So that's going to have me coasting along the x-axis until I get to 0, 0. Well, okay, so that's of this, right? But because y is always 0, this is the same as the limit as x approaches 0 of x squared over x squared, right? Because the y is always 0 in this framework, so the y's are going to go to 0, it's going to leave me that. That limit is clearly 1. Okay, so let's try it from a different direction, right? An obvious choice for the other direction is to try along the y-axis, right? So what's the limit now as we're going to fix x at 0, we're going to travel along the y-axis, right? It goes to 0, 0. So what is that limit going to be? Right? X squared plus y squared, forgot the squared there, squared, right? So here the x's are clearly going to 0, so this is the same as the limit as y approaches 0 of negative y squared over y squared. But that clearly goes to negative 1. And last time I checked, 1 does not equal negative 1, so this limit does not exist because I'm approaching 0, 0 here along the x-axis, here along the y-axis. I'm getting the 1 as the height over here, I'm getting the negative 1 as the height over here, which means that if I go from these two different directions, I'm not pointing at the same value, which means that there is no limit there. Okay, so we're going to prove the existence of a limit. So let's show that a limit exists. Now, this is something that I would never ask you to do on a test. You may have to prove that a limit doesn't exist, but you're not going to have to prove the existence of one. Alright, so typically what we do here is that we show that there is a connection between delta and epsilon. And if you give me the epsilon, I can give you the delta. So basically delta is going to be a function of epsilon. If I can make that connection, I'm able to show that for every epsilon there exists a delta that meets all the conditions that I need to meet. Alright, so let's consider a function. Let's consider the function f of x, y, 3x squared y over x squared y squared, and we want the limit as x, y is approaching the origin. Okay, so this limit actually does exist, but we're going to prove that it does. Okay, so if the limit exists, right, we want to set this up so that if the distance from xy to the origin, right, the distance from x to y, the distance from xy to the origin, sorry, that's what I need there. So this is the distance of xy to the origin is less than delta, right? Then I want 3x squared y over x squared plus y. So the distance between the function and L to be less than epsilon. So I want that to happen. This is what I want, right? Okay, so if I do a little bit of experimentation and I take things along the x-axis like I did before, so the limit as xy approaches 0, 0, right, of 3x squared y over x squared plus y squared. So if I do this along the x-axis, that y is going to be 0. So this is going to be the limit as x approaches 0. Now we make all the y's 0, right? So the top's going to become 0. The bottom's going to become x squared. This thing is approaching 0. So this means that if L exists, then L has to equal 0. Okay, so because all the limits have to exist, one of the limits goes to 0. So whichever direction I'm coming from, they all have to go to 0. Now I want to prove that. Okay, so this means that I want the distance from xy to the origin, right? If that distance is less than delta, then I want this to mean that 3x squared y over x squared minus y squared minus 0, because L would have to be 0, it has to be less than epsilon. So another way you can say this is that 0 is less than x squared plus y squared, because that's the distance, right? Less than delta, and that's going to be positive. If that's true, then we want this guy, and because that's 0, I can just get rid of it, to be less than epsilon. This is what I want to have happen. So every time this value is less than delta, I want that thing to be less than epsilon. So, well, the only thing in this that the absolute value is actually working on is this y right here. So this can be rewritten as that. That's the distance is less than delta. Implies that 3x squared absolute value of y over x squared plus y squared is less than epsilon. Alright, so a little bit of trickery here. Let's just look at this. Right? How do I make that less than epsilon? So 3x squared y over x squared plus y squared is less than epsilon. So that can be written as x squared over x squared plus y squared times 3 times the absolute value of y is less than epsilon. But note, this guy, if you look at it, right, has to be less than 1, because like x squared plus y squared is bigger than x squared, and something bigger over something smaller is less than 1, which means that this thing makes this less than this. So this implies that 3y has to be less than or equal to x squared over x squared plus y squared times 3 times the absolute value of y, which is less than epsilon, right? So at this point, I now have that 3 times the absolute value of y has to be less than epsilon. Okay, so we're getting somewhere here. So what I got here is that if I have the correct distance, then 3 times the absolute value of y has to be less than epsilon. But I can also rewrite this as the square root of y squared, because that's going to give me the absolute value of y, right? So that's there. Okay, but note this. This has to be smaller has to be smaller or equal to 3 times the square root of x squared plus y squared. And this is kind of interesting because I can bound delta with this, right? So this is somewhere around, like, we can kind of like work this out, that this has to be in relationship to 3 delta, because 3 delta's got to be underneath this thing. So let's let epsilon be equal to 3 delta, okay? Another way of saying that is delta is equal to epsilon over 3. Okay, so now I have delta as a function of epsilon. You give me epsilon, I divide it by 3 and say I stretch a delta ball with a radius 1/3 the size of epsilon. And if I do that, I should be able to make the conditions of the limit work. So this follows that for every epsilon, right, greater than 0, delta is equal to epsilon over 3. There exists a delta that's going to work. Okay, so let's take a look at what happens here. Okay, so I have this. I have that the distance from xy to 0, 0, right, must be less than delta, which means that it is equal to epsilon over 3. So this distance is less than epsilon over 3. So that implies that 3, or the square root of x squared plus y squared, has to be less than epsilon over 3. So this implies that 3 times the square root of x squared plus y squared has to be less than epsilon, which now tells me that 3 times the square root of just y squared has to be less than epsilon, because this is less than this, which means that 3 times the absolute value of y has to be, wait a minute, this is starting to look familiar. It's less than epsilon. But because x squared over x squared plus y squared is less than 1, this times 3 times the absolute value of y has to be less than epsilon, which ultimately gets me to 3x squared y absolute value over x squared plus y squared has to be less than epsilon, which implies that, well, this, oh, sorry, there's an x there, right? This is all positive, so this is the same as the absolute value of 3x squared absolute, now I don't need the absolute value anymore. Y over x squared plus y squared is less than epsilon, which means that 3x squared y over x squared plus y squared minus 0 is less than epsilon, which means ultimately, the limit as x, y approaches 0, 0 of 3x squared y over x squared plus y squared must be 0. Huzzah! Alright, we've proven that the limit exists, and we know that the limit is 0, and we've got it. Now, big all caps, you will never need to do this for a test in this class, but it's kind of neat to see that it can be shown. We may make you find a limit, given that the limit exists. We may make you disprove the existence of a limit, but we will not make you prove the existence of a limit in this class, but you have seen the miracle of that here. Alright, so lots of notes there, lots of stuff on limits. We'll look at more of them next class.